Welcome back. My name is Renee Clary, and today we will continue our processes of the hydrologic cycle. In particular, we will be discussing the most powerful agent of erosion, and one agent that played a much bigger part on the Earth than it does today. We're going to be talking about glaciers and glaciation, and even investigate some theories as to why glaciations occur. Let's get started. Glaciers refer to a mass of terrestrial ice. We're not talking about sea ice, but terrestrial ice that formed from recrystallized snow. This mass will move downhill because of gravity. Glaciers constitute 2.1% of Earth's water, which makes them the second biggest repository of water in the hydrologic cycle. So here is our pie diagram, and again, oceans have 97.2% of the total water of the hydrologic cycle, but of the remaining 2.8%, which is right here, glaciers have a whopping 2.15% of that. Glaciers are geologic agents, which means that they erode, they transport, and they deposit. They are the most powerful geologic agent, though today the most effective geologic agent would be running water and fluvial processes because it's much more prevalent than glacial ice. Glaciers are composed of ice, and ice is a mineral. Now, why can it be classified as a mineral by our definition? Do you remember the characteristics of a mineral? Solid, crystalline, naturally occurring, inorganic, definite physical and chemical properties? Yep, ice would be a mineral by this definition. The way glacial ice forms, snowfall is transformed to something called firn, F-I-R-N, to glacial ice. And the process involves thawing, refreezing, compacting, and over time the loss of air spaces. Diagrammatic form, we have snowflakes, a little bit of thawing, recrystallization, we have a granular snow, compaction to firn, and recrystallization and compaction further to glacial ice. Hoar, here we have some snowflakes that have been recrystallized. We have hoar ice here. Firn, recrystallized compacted snow. Glacial ice. Look at the differences here. And finally, here's some melting snowpack. We have two different types of glaciers, two main types, alpine or valley glaciers and continental glaciers, and then there's an intermediate one known as an ice cap, and we'll look at all of these today. An alpine or a valley glacier is simply a river of ice. It's controlled by the shape of the valley it occupies, so therefore it's confined to the valley which it flows through. This is a valley glacier in Alaska, and you can see tributaries are flowing into the main channel. Intermediate between a valley glacier and a continental glacier is an ice cap. It's dome-shaped, a mass of ice, but it's smaller than a continental glacier. This is the Penny ice cap on Baffin Island in Canada. It only covers about 6,000 square kilometers of land. Flow from an ice cap and also from a continental glacier proceeds outward from a center thick mass of ice. So the center of the ice dome is the area where the ice is the thickest, and the ice will flow outward from that center mass. Of course, the largest type of glacier is the continental glacier, It's a large ice sheet. It's not confined to a valley, so it travels outward, again, from a large center mass of thickness outward in all directions. Currently, we have continental glaciers in Greenland and Antarctica, but back in Earth's history, they were much more prevalent and much more pervasive than they are today. Here's an overhead map view of Antarctica. Notice in addition to the continental glaciers, there are also some large ice shelves. They were referred to as barriers back in the days of the early polar explorers. If you look at the shortest distance to the South Pole, there's the South Pole, okay, you'll see that the Ross Ice Shelf immediately below that provides the shortest distance for an explorer to access the South Pole and be first in a race. Interestingly, in the race to be the first person at the South Pole, Roald Amundsen, the Norwegian, overwintered, established his base camp on the Ross Ice Shelf. His rival, Robert Falcon Scott, did not want to overwinter on the ice because he thought it would be a dangerous situation, so therefore he camped on solid ground. So Amundsen had an obvious advantage, and he was the victor in that race. There's the Ross Ice Shelf. Here is a view of the Antarctic Continental Glacier. The rocks that are sticking above the ice are mountain peaks that are not covered by ice, and these are nunataks. The glacial budget refers to gains and losses made by a glacial system. There are two zones in a glacier, a zone of accumulation and a zone of wastage. The zone of accumulation is that area where the snowfall exceeds the losses. So the amount added to the glacier exceeds the amount lost by melting, calving of icebergs, sublimation are all ways that glaciers can lose ice. The zone of accumulation is that area where the snowfall actually exceeds the amount lost. It's covered by snow year-round, and it's separated by the zone of wastage, the lower zone, by the firn limit. The zone of wastage, on the other hand, has more loss than gains. Loss again from melting, sublimation, where ice goes from a solid directly into the vapor phase, or calving of icebergs at the terminus of the glacier. Now, what happens, you think, if the zone of accumulation is greater than the zone of wastage? When that happens, we actually have a glacier that is growing. What if the zone of accumulation is less than the zone of wastage? In that case, the glacier is retreating. Now, what happens if the zone of accumulation, the amount added by snowfall, is equal to the amount that's lost through melting, sublimation, and calving? We have a balanced budget. If only our government could do the same. Let's see some diagrams of this. Okay, here we have winter accumulation and snow melt are all going to be equal, so this is going to be a glacier with a balanced budget. The firn limit, it's shown with that little dot in the diagram, that's the limit where the area of accumulation, the zone of accumulation, is separated from the zone of wastage. Now in this diagram, what do we see happening? The terminus, or the toe of the glacier, is actually retreating. There's more melting than snowfall. So the glacier is retreating, and we have a negative budget. Conversely, we can have more snowfall than melting, so the glacier can actually be growing. This could be a positive budget because the terminus is advancing. Here is a painting from 1826. Samuel Biermann painted this view of a glacier in Switzerland. So check out the relationship between the terminus of the glacier and the valley floor, and use this rock face as a marker. Okay? So keep in mind where the terminus of the glacier is with respect to that rock face. Here's a photograph of that same glacier in 2007. The terminus now is hidden behind that front rock projection, but here's our rock face to compare. This glacier would have a negative budget over the past 180 years. How do glaciers move? Well, at about 40 meters in depth, the overlying mass of the ice, the stress of the ice, results in strain. We can see that resulting in plastic flow. In this case, the ice is going to stick at the bottom and sides of the valley, but the middle will flow. The friction of the channel, the bottom of the valley and the sides, will prevent that ice from flowing very well, but the middle tends to flow. The top layer of the ice is brittle, and it will develop these long fractures known as crevasses. Ice can also move forward by basal slip. Liquid water is involved in this case and facilitates the slip, and the whole mass of ice will suddenly move forward or surge forward. There is a pressure melting point that is reached where the ice at the bottom will melt, and the layer of water at the bottom of the glacier will lubricate the ice, and you will see the ice moving forward on a layer of water. Note the crevasses at the surface here. The crevasses will open up with tension as the ice moves over a slight topographic, in this case it's like a little mound, and then as that ice moves down the slope, the compression of the ice causes the crevasses to close. But there is a brittle zone on the upper surface of the ice, whereas there is a zone of plastic flow toward the base of the glacier. Now, if snowfall covers those crevasses, it can create a very dangerous situation for humans. The snow bridge will hide the crevasse below and may not hold the weight of a person crossing the crevasse. Douglas Mawson led a very famous expedition to the South Pole. He was there at the same time that Amundsen and Scott were racing for the geographic South Pole. Mawson instead was investigating the magnetic South Pole and was also mapping new territory. Well, he and two colleagues set off to map some pretty treacherous terrain. And he was, one day he was riding on a sledge pulled by dogs, and his colleague Ninnis was also riding on a sledge behind him pulled by dogs. And the second colleague, a fellow by the name of Mertz, was actually going ahead on skis to sort of test for these snow bridges to see whether or not the weight of the sledges, the weight of the men and their supplies would be carried across this very treacherous terrain. Well, Mawson recalled it by saying that, Mertz turned around and started waving, and when Mawson turned around to look at the sledge that was supposed to be behind him, it was gone. So Mertz and Mawson went backwards and then found a crevasse. And at about 100 feet below the surface, they saw a dog whose back had obviously been broken in the fall, but they couldn't see the bottom of the crevasse. These can extend very, very, very far into the ice. Now, not only was this tragic because they lost their colleague in this snow bridge accident, the snow bridge held for both Mertz, who was going over on skis, and Mawson, who was going over on a sledge, but it didn't hold for Ninnis. So they tragically lost their colleague, but also on that sledge was their tent and some very important supplies of food to get them back to civilization, or to base camp. I don't know if we could call Antarctica a civilization at any point. But in any case, Mawson ended up being the only survivor, because on the return journey, Mertz is the first person who succumbed to documented vitamin A poisoning. Very tragic story. These crevasses are in the Exit Glacier, Kenai Fjords National Park and Preserve in Alaska. Here's an ice fall in the Jungfrau in Switzerland. This happens when the ice breaks up as a crevasse glacier moves down a steeper slope, and these ice blocks kind of break apart. More crevasses. And they can extend very far below the surface of the glacier. Very, very dangerous. Note that the friction at the side and bottom of the channel keep the ice from moving more rapidly. The way that scientists figured this out was very simple but very brilliant. They placed those orange traffic cones in a straight line across the glacial channel and observed the distance that the cones moved at successive time intervals. And so they noticed that the central cones moved faster and the side cones were moving slower and progressed the way you see those arrows progressing in the diagram. The rate of movement of glaciers can be anywhere from a few centimeters to several meters a day, and periodically some glaciers experience surge, and these are short episodes of very, very fast flow. For example, here we have the Hubbard Glacier in Alaska. In 1986, it surged across the Russell Fjord and isolated the fjord from the open sea. It ended up stranding some animals. Let's look at how glacial ice serves as a geologic agent by eroding, transporting, and depositing. All geologic agents erode, transport, and deposit. Erosion by glaciers includes bulldozing, plucking, and abrasion. Bulldozing is just what it sounds like. The glacier is pushing rocks in front of it like a big bulldozer. Plucking occurs when the water freezes in cracks and pulls the rock loose. This results in something known as a roche mountainée, which means rock sheep in French. Abrasion can result in glacial polish, a very smooth surface, or striations. The glacial ice at its base may have different rocks that are entombed in the ice and will scratch along the underlying bedrock to produce striations. Here we see the development of a roche mountainée. In this diagram, the glacial ice is polishing and abrading the upstream projection, which is off to the right, and then plucking the downstream projection. So the ice is moving from the right to the left in this diagram. It's abrading and polishing to the right and plucking on the downside. Here's the Roche Mountainée in Montana. Can you pick out the direction that the glacier moved? I don't think it's that easy in this photo, but the glacier moved from right to left. It plucked the left side of that projection. Here we have some glacial polish and striations at Devil's Postfall in California. Remember these features from an earlier video lecture? Those polygonal structures formed when lava cooled and contracted. We have several erosional features in valley glaciers, and we'll take a look at those. Glacier valleys differ from river valleys in their shapes. Glacier valleys have a broad U shape, while river valleys typically have a V shape from erosion of the channel. The water is responsible for the removal of material directly above the channel, but mass wasting of the side material will account for the removal of the rest. But that produces a V shape, whereas in a glacier we have these broad U shapes. We see features such as hanging valleys. Hanging valleys result when a tributary glacier valley connects to the main glacier valley, but the tributary is not at the same depth as the main valley. So any stream running through the little tributary valley will result in a waterfall, so this is a hanging valley. I'll show you a picture of that. A fjord refers to a drowned glacial valley. The ice carved out a channel. The sea level has subsequently risen and flooded that channel and resulted in a fjord. Here we see a large U-shaped glacial valley in Montana. There it is. And there's another one in Germany. The fjord at the bottom photograph in Norway, right there, is a glacial trough that extends below sea level, and now it's flooded. Here's a hanging valley. This is Bridalveil Falls in Yosemite Valley National Park. It plunges from a hanging valley to a larger U-shaped glacial trough below. So let's pick out the tributary or hanging valley right there. And the larger glacial trough, the main channel in this case, was right there. So a much bigger river of ice down in the lower valley and a smaller tributary connected to it, but at a different level. The surfaces were the same, but unlike a river system, the base level of the tributary was not dictated by sea level. We're looking at ice, which is much more powerful than running water. Cirques are bowl-shaped depressions. Horns are steep-sided peaks, and arêtes are linear knife-edge ridges. So in these photographs, you can check out the cirque in the top photo. This is on Mount Wheeler. There it is. That's a cirque. Now, when the cirque on Lassen Peak was filled with water, a torn, T-A-R-N, formed. In this case, it's known as Lake Helen. The horn being depicted is the Matterhorn in Switzerland. And finally, the bottom photo features an arête. This is a knife edge ridge. Can you pick out any horns, arêtes, and cirques in the Alps? See several horns, very steep peaks, and arêtes are simply those knife edge ridges. One in the center of the photograph. Cirques are bowl-shaped depressions. Truncated spurs form when ice has carved out a glacial valley and leaving behind the remains of former ridges. Here we have an unglaciated topography, strained by streams. So the erosive agent here, the geologic agent, was running water, and then the area was subsequently glaciated and covered by ice. Note the broad U-shaped valley. Compare that to the V-shaped valley off to the left. They're different shapes. And once the ice melts, the resulting topography looks noticeably different from the original. Note that the peaks now are very jagged, very steep. Those are horns. The arête is that knife ridge. The truncated spurs, again, those form once the ice has kind of carved out the glacial valley and left behind just a kind of an erosional remnant of the ridge. What about the effects of continental glaciation? Well, this is an ice-scoured plain in Canada. Continental glaciers tend to smooth, abrade, and strip off the soil. So we end up with very subdued topography instead of those steep peaks and arêtes and horns. You end up with lakes in this ice-scoured plain, bedrock exposure, and the drainage, because the drainage system is not developed, is a deranged drainage system. What about transportation? Well, sediment from the valley floor is carried near the base of the glacier, of an alpine glacier, whereas sediment falling from the valley sides through mass wasting processes are carried on the top surface. And again, this is the most powerful agent of erosion. As the river moves, this ice river moves down its channel, if it encounters a big boulder, the pressure causes the ice to melt, and then the water refreezes around the boulder, and it's simply plucked up and carried along. So not too much stands in the way of a huge glacial body of ice. The ice in this photograph appears dirty, and that's because the sediment it's transporting is on the top of the ice surface. So this was added by mass wasting processes. As the most powerful agent of erosion, a glacier can transport sediments from the finest ground rock particles all the way to large boulders. Much more powerful than running water. When the rock is pulverized as the glacier ice moves through, we end up with something called rock flour, very finely ground rock. It's produced by glacial abrasion, and it's transported out of the system with meltwater from the glacier. This stream in Switzerland looks kind of milky in appearance, but that's because of the rock flour that's being transported in suspension. What about deposition? Glacial drift refers to all deposits that are deposited from glacial activity. And we can divide this into two types. Till is deposited directly by glacial ice. It tends to be unsorted because glaciers do not sort. Think how a glacier deposits. It melts. So anything that was entrained in the ice, from large boulders, cobbles, sand, even fine sediment that's being carried on top, or ground rock flour at the base, is suddenly just deposited in a heap as the ice melts. So it's not sorted. It's not well rounded either. It tends to be very angular because the ice does not allow for that polish of the sediments as they roll around in the case of running water. Instead, they are either carried along the base or they're carried along the top surface of the glacier, entrained in the ice. So it's not that there's a whole lot of tumbling going on here. A glacial erratic is a large boulder that's carried by a glacier, and we know it's moved by a glacier because it's very different from the underlying bedrock, and these can be huge because ice is a very powerful geologic agent. I'll show you a picture of one in just a minute. Stratified drift is the other category of glacial drift. Again, we can have till, which is deposited directly by the glacier and it's unsorted, whereas stratified drift is sorted by streams. It's the meltwater. This is Pleistocene till off the east coast of England. Note that there are big pieces that they look pretty angular, don't they, in finer stuff. So it's a jumble of unsorted sediments that are deposited directly by a glacier. And this is an erratic. This is the Airdrie erratic near Calgary, Alberta. It's 14 meters long and 7.5 meters tall. There's a human for scale. Again, glaciers are the most powerful geologic agent. This is a very big boulder that was transported from its original area by glacial ice. This is outwash gravel and sand in northern England. Because it is outwash, it was transported by some meltwater, so there is some stratification evident here. You can see different layers, layers or bedding of very thicker particles and then some finer stuff. But it's sorted by running water. Glaciers do not sort. Till deposits include moraines and drumlins, and let's look at each of these. A moraine is a deposit made directly by a glacier. An end moraine would be the rubble or the pile, the debris pile at the terminus or the end of a glacier. The terminal, of course, would be the outermost end moraine. This is the farthest the glacier ever reached and left behind its rubble pile. But sometimes with a negative budget, the glacier terminus is retreating. And in that case, we have a recessional moraine. The ice front recedes and there's a new moraine or a new rubble pile behind that terminal moraine toward the start of the glacier. So the glacier is receding. A ground moraine, on the other hand, is till deposited as a flat layer, a thin layer, it's not a ridge, at the terminus of a glacier. Let's look at that in more detail. Here's an older diagram. The farthest reach of the glacier is marked by that unconsolidated till deposited directly by the glacier. So this is a terminal moraine. The glacier is experiencing a negative budget, so it's going to be retreating, and the melting ice leaves behind a ground moraine. Okay, and note it's not a ridge, it's a sheet-like deposit of till as the ice melts. And a new terminus is established behind the terminal moraine, and so this would be a recessional moraine. Here we see a terminal moraine, and now the glacier is retreating. It will establish a new moraine at the toe of the glacier, so that will be a recessional moraine. Okay, other than end moraines, we can also have lateral moraines. This is deposition along the margin or channel of a glacier, and a medial moraine will result when two lateral moraines collide or merge. This glacier on Baffin Island, Canada, has deposited a lateral moraine, and there it is right there, along the channel, the side, and also an end moraine. There it is, at the terminus. Again, lateral moraines form along the side of a glacier. This is Bernard Glacier in Alaska. And a medial moraine will mark where the two lateral moraines come together, along with that merging ice. This block diagram illustrates the sediment carried along by a glacier deposited as a ground moraine down at the bottom, lateral moraines at the side, and medial moraines as those two laterals come together. Okay, we said that till deposits include moraines and drumlins, and we've discussed moraines, but what are drumlins? Drumlins are till that has been reshaped into elongated hills, and they can tell us the glacial flow direction. Here's a great older diagram. It shows you that the shape of a drumlin mimics that of an overturned spoon. And you can see the ice sheet, in this case, moving from kind of the northwest, and it's reshaping that till into this kind of hill-like structure, steeper side upriver, up ice as opposed to down slope. Now here is a drumlin. What do you think the direction of the glacial flow was? If you said from the right, you are correct. Now, stratified drift are those deposits that are modified by meltwater, running water, because glaciers do not sort. I can't stress that enough. Glaciers simply melt and the ice deposits the rubble. But stratified drift involves meltwater, running water. These deposits include kames and eskers. A kame is a hill of stratified drift, whereas an esker is a sinuous ridge of stratified drift. Eskers form in tunnels beneath the ice as running water moves. These little rivers beneath the glacier transport sediments out. This is a kame. It's in Wisconsin. Okay, now wait a minute. We have three hill forms associated with glaciers. We have drumlins, we have roches-montagnais, and we have kames. So how do we tell them apart? Okay, think about this. Start with the roche-montagnais. It's an erosional feature. It is solid rock that was shaped by the moving ice. It is an erosional feature. So that leaves us with drumlins and kames, which are both depositional features. But we can tell them apart because a drumlin is unstratified drift. It's till. It's a reworked moraine, so therefore it's not sorted. A kame is stratified, so obviously there's some water involved because ice does not sort sediments. Okay, so that's how you tell them apart. This is an esker in North Dakota. Note the sinuous serpentine shape of that. And this esker in Canada was revealed in 1992 with melting ice. We also have glacial lake formation and glacial lake features. Kettle lakes form when a retreating glacier leaves behind a block of ice, and the weight of that block of ice depresses the sediments below, and then the meltwater from the block of ice fills up this depression. But if the depression subsequently is intersecting the water table, of course the groundwater will recharge and you'll end up with a kettle lake. When you have a glaciated landscape, we get lake deposits known as varves, and varves consist of an annual light and dark deposit band. The light layer forms during the summer, and it consists of clay and silt. Again, these are fine sediments because they're lake deposits. The dark layer forms in the winter, and that consists of clay and organic material. In the winter, we don't have the biological activity that we do in the summertime, therefore we get this dark organic layer. We can also see these lake deposits interrupted by drop stones, and these are simply larger particles that were floated out in an iceberg, and then as the ice melts, the ice drops its sediments, hence the name drop stone, and these larger stones end up in the middle of a lake. Here are some kettle lakes. And check out these varves. We see the light and dark laminated layers. The drop stone, there we go. Look how it depresses those layers below it. And again, that's a rock that was rafted out in ice, and as the ice melted, it released that nice drop stone into the lake. Here we see a drop stone, kind of a rectangular block. This is late Precambrian glacial marine and ground moraine tillite in Namibia. In this case, it looks like we have stratification in a marine setting below the drop stone, but there's some till above that. Look at the unsorted stuff above that drop stone. There have been times in Earth's history when more of the land surface was covered by glacial ice. Whenever ice sheets form, the sea level will fall. And then when the glaciers and the continental glaciers and ice sheets melt, the sea level will rise. Ice also causes continents to sink into the mantle. The additional weight, if you remember the principle of isostasy, the extra weight causes that crust to depress into the mantle, but when glacial ice is receding or we have melting, then the continent will slowly rebound. The last ice age started about 1.6 million years ago, and this is the Pleistocene epoch. This is the ice age of the Pleistocene. There were 4 major glaciation pulses, and they are identified by the farthest reach of the ice in North America. The most recent event ended about 10,000 years ago. Now, Pleistocene glaciation is shown here in these diagrams in the northern hemisphere for North America on the left and Europe on the right. And contrary to some popular belief, the entire United States was not completely under ice. Note that the Gulf Coast states, the eastern coast, and over on the west coast as well, the continental glaciation did not extend over the entire continent. Now, during the last ice age, about 18,000 years ago, sea level was about 130 meters, about 400 feet lower than it is at the present. So the continental shelves were exposed. The shoreline was near the continental shelf edge, but melting of the glacial ice caused sea level to rise, and you see the current outline of the U.S. coastline now as that kind of black dotted line. If the remaining glacial ice is melted on Earth, the change in sea level would rise another 65 meters, and this shows you what North America would look like. The shorelines would be very, very different. During the Pleistocene, most of the world was drier during the accumulation of the ice, but there were other zones that were much more humid and tropical than they are today because the zones were compressed toward the equator. So therefore, where we see deserts today were lush and tropical during the Ice Age. Well, not necessarily tropical, let's say temperate. Pluvial and proglacial lakes formed. What's the difference between these? A pluvial lake forms with cooler temperatures and wetter climates, but it's away from the glacier. It's at a distance from the glacier. Proglacial lakes, on the other hand, form as the meltwater accumulates along the margins of the glacier. So proglacial lakes form near the glacier, pluvial lakes form farther away from the glacier because of cooler temperatures and wetter climates. Here are some pluvial lakes during the Pleistocene in western North America. Note how large Lake Bonneville was. There it is. I circled it for you. The remnant of shrinking Lake Bonneville is the Great Salt Lake in Utah. You can see that it's a lighter color, much, much smaller than the pluvial lake of Bonneville. The Great Lakes are proglacial lakes, so they formed via erosion at the terminus of the glaciers. As the ice retreated, the basins began filling with meltwater. So here we have the ice sheets 13,000 years ago and 11,500 years ago. Note the retreat, and now these huge lakes are forming. 9,500 years ago, ice is retreating, and 6,000 years ago. This is an interesting photograph. These giant ripple marks, actually they're gravel deposits, in Montana formed when proglacial Lake Missoula suddenly drained. The ice dam holding the lake in place failed, and a lot of water came out in a torrential flood. What causes glaciation to occur? Well, in the past, climatic changes have occurred on numerous occasions. Short-term climate changes can be attributed to excessive volcanism, eruption of pyroclastics in the atmosphere, which blocks out sunlight. Long-term climate changes, on the other hand, are closely linked with plate tectonics because the landmass has to be far enough north or south on a pole in order to accumulate ice. Also, when we have collisions, such as continental convergent plate boundaries, we have uplifted areas, and the higher removed you are from the Earth's surface, the higher in elevation, the more likely you are to accumulate ice. But what about those intermediate climatic changes? Well, the Milankovitch theory accounts for irregularities in the Earth's orbit and solar radiation changes as causes for intermediate climatic change. In particular, Milankovitch looked at 3 different variables in the amount of solar radiation reaching the Earth's surface. Orbital eccentricity occurs on about 100,000 year cycle, and this refers to the Earth's orbit being in almost a circle versus an ellipse. And this occurs, again, in about 100,000 year cycle interval. Axial tilt, the axis of the Earth, will progress over time so that whereas the tilt may be 20 degrees, the tilt will reverse itself almost completely 90 and then move in the other direction. This is on a 41,000 year cycle, axial tilt. And finally, we have the precession of the equinoxes. This occurs on a 23,000 year cycle. Let's take a look at that. Right now, the Earth is actually closest to the Sun in January. For us in the northern hemisphere, the winter is when the Earth is closest to the Sun. So the Earth's orbit, again, varies from a circle to an ellipse and back every 100,000 years. The Earth's axis of rotation will change its position. Note the tilt at 23.5 degrees. The axis 11,000 years from now is going to be in the opposite 23.5 degrees. So when do we have summer in the northern hemisphere? Okay, we have summer in the northern hemisphere when the earth is farthest from the sun. And in January, when the northern hemisphere experiences winter, the earth is actually closer to the sun. Now this diagram is greatly exaggerated. So why do we have summer if the earth is actually closest to the sun in January and farthest from the sun in July? Well, there's a great video called A Private Universe, and Harvard graduates were being interviewed and asked, why do we have summer? And they invariably said, because we're closest to the sun. Now that's wrong. Okay, you can see in this diagram that's completely wrong, that's completely erroneous. We are closer to the sun in the northern hemisphere when we experience winter. So summer, we're farthest from the sun. So the northern hemisphere is farther from the sun during the summer, but we're tilted toward the sun and therefore receive more direct solar radiation, and that's why we experience summer in the northern hemisphere. So what will happen when we experience our winters in the northern hemisphere when we're farthest from the sun? How might that affect glaciation? We suspect there would be increased glaciation. And why would it matter for the northern hemisphere as opposed to the southern hemisphere? Note I've been saying northern hemisphere. Well, think about it. Remember, glaciers form on continents. This is a terrestrial ice mass. And where is most of the continental mass associated? The northern hemisphere. Okay, so there's a much greater density of continental crust in the northern hemisphere than the southern hemisphere. Therefore, if the northern hemisphere is farthest from the sun in winter, we have increased chance of glaciation. And this diagram kind of sums up Milankovich's variables. Again, we have orbital eccentricity. We're looking at the tilt of the Earth and the precession of the equinoxes as being the three main variables for these intermediate climate changes. Plate tectonics are responsible for the long-term climate changes, and short-term climate changes can be the result of volcanic eruptions, for example. Well, that is going to conclude this discussion today on glaciers and glacial processes. We will continue the hydrologic cycle and other video segments. We have groundwater, we have running water, and shoreline processes. Thank you so much for joining me today. It was only meant as an overview, so if you have any questions, please feel free to post them on discussion boards or email your instructors. Have a great day.